Hello, welcome to today's lesson. Today we're going to start section 4.7. We're going to be talking about inverse trig functions, and we're going to start with the sine function. So this is not inverse sine. This is just regular y equals sine of x. Its domain is all real numbers. Its range goes from -1 to 1, including -1 and 1. And if we're interested in finding the inverse, the first thing we want to do is check to see if this function is 1 to 1. This is a function because it passes the vertical line test. No matter where I put a vertical line, it's never going to hit the graph more than once. However, it fails the horizontal line test because if I put this horizontal line in, it hits the graph many times. And it actually doesn't intersect the graph just at those 5 points. It intersects the graph an infinite number of times because this graph has a domain of all real numbers. So every time those hills and valleys repeat, you cross that horizontal line again. So this graph is not 1 to 1. It fails the horizontal line test. That means if we find the inverse right now, it won't be a function, and we like functions. So we have two options here. We can either say, okay, the inverse won't be a function. We give up. Let's just move on to section 4.8. Or we can say, let's restrict the domain and find the inverse of that portion of the graph. So that's what we're going to do. We're not going to give up. Some graphs are just too common or too special. We've spent so long talking about this sine function. We want to force the inverse function to exist. So let's restrict that domain. So what we want to do to restrict the domain is we want to find a portion of this graph that is 1 to 1. So some ideas you might have. You might first think 1 full period from 0 to 2 pi, but that won't work because that still fails the horizontal line test. If you put a horizontal line right through here, it hits more than once. Okay, so that won't work. We can't go 0 to pi, still fails the horizontal line test. We can go from 0 to pi over 2, because that piece is 1 to 1, but we can take more than that. So looking at this graph, what we can do is we can actually go from negative pi over 2 to positive pi over 2, and that piece right there is 1 to 1. Oops, that piece right there is 1 to 1, and it actually covers the entire range as well, because it goes all the way from -1 up to +1. So even though it's a little teeny tiny part of the sine graph and it doesn't really even look like sine, it covers the range, and it's the most we can take while maintaining that it's 1 to 1. Because even if I went from negative pi over 2 out to like that far, that's no longer 1 to 1. So we have to be very strict that we're 1 to 1 on this. And if you're looking at that and thinking, could I go from pi over 2 to 3 pi over 2? Yes, that piece would be 1 to 1, and it would also cover the entire range, but it's not the piece we use. If you look in any math book in the world, the piece of the sine graph that we're going to use to find the inverse of sine is that one right there. So what we're looking at is a restricted domain of negative pi over 2 to positive pi over 2. And it covers the entire range of -1 to 1. So what we're going to do in order to graph the inverse is I'm actually going to have us first do what I call a zoom in. We're going to graph just this part of the graph down here so that we can take a look at the characteristics and get ready to make the inverse. So this is a step I like to take in the beginning. Once you've done this once or twice, you'll probably skip this step. So taking a look at this graph and just zooming in on that piece of the one that I highlighted in red. Okay, so first on the x-axis, we're going from negative pi over 2 to positive pi over 2. And I'm going to try to be a little precise here about my measurements along the x-axis and y-axis. I'm not going to take out a ruler because I'm not going to worry that much about it. But if you look, this is about the same as that. That's pretty good. And then my range is going to go from -1 to 1. And here's what I'm going to be careful about. And I've never really drawn your attention to this before. If we look, this right here is pi over 2. That's about 1.5. So if you can picture where 1 is, it might be right about there. So if that's what 1 would be on the x-axis, let's try to make 1 on the y-axis about the same. And I've never drawn your attention to that before. Usually if you were going to do a sketch without graph paper, you just kind of put your tick marks, try to evenly space them. But you wouldn't really worry about whether 1 on the y-axis is the same as 1 on the x-axis, because they don't have to be. But for this particular topic, I'd like us to pay a little bit of attention to that. Okay, So I'm just recopying this graph here. So I have a point at pi over 2, 1. I have a point that goes right through the origin at 0, 0. And we have a point right here that's at negative pi over 2, negative 1. And this portion of the graph right here is concave up. And this portion of the graph right here is concave down. And that is not the inverse of sine. That's my zoom in piece on sine with the restricted domain. Now we're ready to graph the inverse. So to graph the inverse, I would do that right underneath the sine graph here, but I'm going to actually do that over here so that we can see both at once. So the inverse of sine, there are two notations for it. You can use this, it looks like sine to the negative 1, but that's not a negative 1 exponent. That's a notation for inverse. Or you can use what we call arc sine. So the actual word arc sine would have an E on it, just like how sine, this is an abbreviation for the word sine. So arc sine is abbreviated ARCSIN without the E. So the actual word has an E, the abbreviation does not. And these are interchangeable with each other. So if you ever see sine inverse, it means arc sine. If you see arc sine, it means sine inverse. Completely interchangeable. And in order to get the graph of arc sine, what I'm going to do is I'm going to use the zoomed in picture of sine, and we're going to use our properties of inverses. That's why we took the time to review them. So what I like to do first is switch the domain and range. So my domain for this graph, the restricted domain went from negative pi over 2 to positive pi over 2, and the range went from negative 1 to 1. So that means for the inverse, the domain will be from negative 1 to 1. And the range is going to go from negative pi over 2 to positive pi over 2. So after I switch the domain and range, I like to set up my axes. So if I think about the axes that I'm going to need, I'm going to need to go from negative 1 to 1 on the x-axis. And I'm going to have to go from negative pi over 2 to positive pi over 2 on the y-axis. And again, I'm going to try to just pay attention to if this is 1 unit on the x-axis, let's try to make the same for 1 unit on the y-axis. But I actually don't need to indicate the tick mark at 1. I need the tick mark at 1.5, around 1.5, 1.57 approximately. And then whatever this distance is, I'm going to go about the same distance down for negative pi over 2. So like I said, we're not so concerned with precision. I'm not taking out a ruler to do this, but I just kind of want to be aware that if this is 1 on the x-axis, I'd like 1 on the y-axis to be about the same. Okay, so we switched the domain and range and set up the axes. Next, I'm going to reverse the x and y in the ordered pairs. So if you notice, I indicated the ordered pairs for each of these critical values here. So this end point is pi over 2, 1. So on the inverse, we're going to have 1 pi over 2. And if we go through 0, 0 for the regular function, if we reverse the x and the y, we're still going to go through 0, 0 for the inverse. And instead of negative pi over 2, negative 1, we're going to have negative 1, negative pi over 2 for the inverse. And then we need to connect these dots. So to figure out how to connect the dots, there's kind of 2 ways to go about thinking about it, in my opinion. One is to visualize the line y equals x going right through this graph. If you can visualize the line y equals x going through this graph, I think you'll see what happens to these 2 pieces. That's that the concavity is going to reverse. So if you look at this graph, the regular sine graph on the restricted domain, from left to right, first it's concave up and then concave down. Concave up, then concave down. So for the inverse, it should be reversed. It should go concave down and then concave up. And that's what the graph of inverse sine looks like. So to know about the concavity, those of you that can visualize flipping this graph over the line y equals x, that's great, go for it. and then you'll know that the concavity reverses, or you can memorize that the concavity reverses. Just like the domain and range switch and the ordered pairs, the x and y reverse, the concavity is going to reverse as well. And this is our graph of inverse sine. I'd like to take you over to Desmos to show you that graph together with the graph of arc sine, regular sine and inverse sine. So here's the graph of regular sine. That's just a small piece of it. And here's the graph on the restricted domain. So that red part is the restricted domain we used. So if this is 1 and this is 2, this is about 1.5. That's about 1.57. Okay, similarly out here, that's at negative pi over 2, where we have, oh, forgot I have the ordered pairs for you. Okay, so there's sine on our restricted domain. And here comes the graph of arc sine, or inverse sine. And as you can see, they are indeed reflections of each other over the line y equals x. They're very close together in this region, so it's kind of hard to draw. That's why I went over to Desmos instead of trying to draw it by hand for you. So taking a look at the graph that we made, this is the graph of inverse sine. And just to note, some of you might be thinking, okay, so what do we do next? Are we going to do transformations on this? And the answer to that is no, we actually don't. You could move this up and down and left and right, stretch and shrink it, reflect it. But we don't do that with this inverse sine graph. What we're going to be doing starting tomorrow is doing some other types of problems with it, using the information that we have here. So just kind of observing what the graph of inverse sine looks like. All right, let's continue on to inverse cosine. And now that we've done this once, we can move a little quicker through the next ones. Okay, so here is regular cosine, and we want to graph inverse cosine. So as we can see, it's not 1-to-1. We need to find a piece that's 1-to-1. For sine, we used from negative pi over 2 to positive pi over 2, and that's not going to be appropriate here. That piece that I'm looking at still fails the horizontal line test. So taking a look at the graph of cosine, can you predict what we're going to use for the piece that's 1-to-1 to find the inverse of that piece? We're going to use 0 to pi. If you look at 0 to pi, it covers the entire range because it goes from -1 up to 1. And that piece is 1-to-1 because it passes the horizontal line test. We can't take any more because if we take even just a little bit more, we're going to fail the horizontal line test right down here. And we don't want to take any less because if we take less, we don't cover the entire range. We stop short of that -1 on the y-axis. So this is the piece we're going to use. If you're wondering, could we use from pi to 2 pi? Yeah, technically you could. You could go from negative pi to 0 as well. But the piece that we use, no matter where you live, no matter where you're learning this math, we're going to be using from 0 to pi. So this is cosine. Cosine's actual domain is -infinity to positive infinity. The range is -1 to 1. But the restricted domain that we're going to use goes from 0 to pi. So let's zoom in on that piece. And again, this is a step you'll probably find unnecessary once you've done this once or twice. But to zoom in on this piece of the cosine graph, I would like to observe that we actually don't need anything to the left of the y-axis. So when I go to set up that graph, I don't really need much space over here to the left at all. We have a point at 0, 1. So if that's 1 on the y-axis, we have a point at pi over 2, 0. So if that's 1 on the y-axis, I kind of want my 1 to be the same on the x-axis. So pi over 2 might be about here, about 1.5. And that's pi over 2, 0. And then we have a point at pi -1. So if this is pi over 2 on the x-axis, I want to go about double that to get to pi. And if this is my 1 unit on the y-axis from here to here, I want about the same to get to -1. And then looking at the concavity of the original from left to right, it's concave down and then concave up. So for my graph from left to right, I'm going to go concave down and then concave up because I'm not finding the inverse yet. We're not graphing the inverse yet. We are just zooming in on that piece of the cosine graph that we're going to find the inverse of. So this is still cosine. And we're zooming in on that piece. And that piece might look very different than the piece up here. And one of the reasons for that is what I talked about the scale on the x-axis and the y-axis. See, the scale on the x-axis here, this is 1 unit. But here, this is pi over 2, so 1 unit on the x-axis might be about there. So if you look, it's inconsistent from x-axis to y-axis. This is about 1 on the x-axis, but this is about 1 on the y-axis. And it's okay to do that in a graph, but for this particular topic, I like you to see the graph where it looks approximately the same for 1 on the x-axis as 1 on the y-axis. All right, now we're ready to find the inverse. So using the same steps as before, to graph inverse cosine, which is also known as arc cosine. And arc cosine does have 2 C's there. It's arc cosine. All right, and these are interchangeable. We're first going to switch the domain and range. So instead of having a domain from 0 to pi, we're going to have a domain from -1 to 1. And our range is going to go from 0 to pi. Because what I'm doing is I'm switching. That restricted domain becomes the range for the inverse, and the range becomes the domain for the inverse. So now that I switched domain and range, the next step I gave was to set up the axes. So thinking about the axes, we need to go from -1 to 1 on the x-axis. For the y-axis, we have to go from 0 to pi. So we actually don't need anything below the x-axis. So as you go to set up your graph for the inverse, if you keep that in mind, you might set up your graph, your axes, a little bit more like this, because you don't need anything down here. So on my y-axis, I want to go from 0 to pi. So if this, let's make that pi, then halfway would be pi over 2. And if that's pi over 2, let's visualize that's about 1.5. So 1 might be about here. So if that's 1 on the y-axis, then I want 1 on the x-axis to be about the same. And that would be -1. Okay, so the steps I gave, switch the domain and range, set up your axes, reverse those ordered pairs. Instead of 0, 1, we'll have 1, 0. Instead of pi over 2, 0, we'll have 0 pi over 2. Instead of pi -1, we'll have -1 pi. And concavity will reverse. So from left to right, if this is concave down, then up. Left to right, concave down, then up. From left to right, when you connect these dots, you're going to go concave up to concave down. And that's your graph of inverse cosine. Let's take you over to Desmos to show you what that looks like on the same plane, cosine and inverse cosine. Okay. So here's part of our cosine graph. That's not very much of it. I'm not going to change my window here because I just want to show you the inverses. But here's the restricted domain. Okay, I am going to change my window. All right, there we go. So here is your graph of cosine, and here's the restricted domain. The restricted domain for cosine goes from 0, 1 through pi over 2, 0 out to pi -1. So that's the piece we're looking at. And what we want to do is reflect that over the line y = x. And when we do that, we get our inverse cosine graph. And so the blue one there is inverse cosine. And you can see they are reflections of each other. This little piece reflects over and gives you this guy here. And this longer piece of that red cosine graph reflects over and gives you this piece of the inverse cosine graph. So again, I think it can be tough to draw on the same plane. So that's why I take your Desmos instead. Another thing I'd like to mention about this graph before we continue is when it comes to concavity, I usually just remember it reverses. So if it's concave down, then concave up. It goes concave up, then concave down. But something else I'd just like to make you aware of. If you kind of tilt your head, turn your paper, what you'll see is if you were to continue this graph, so if it didn't just end right there, what you, I hope, would see is you'd see that you kind of have like a cosine graph running up and down the y-axis. And that should actually make sense, because if we had never restricted the domain of cosine, so if we hadn't restricted the domain of cosine and we found the inverse of the entire cosine graph, what you would get for inverse cosine is you would get what looks similar to a cosine graph running up and down the y-axis instead. But we can't have this dashed piece as part of our inverse, because then we'd fail the vertical line test. So that's why for the inverse, we only look at this part. But I like to bring that up because sometimes that helps people remember the concavity as well. Because when you look at the graph, it should remind you of a cosine graph. If you were to have your concavity opposite, when you look at this, it just doesn't look right. It doesn't have that smooth hill and valley shape that we see. So that's just another option to remember the concavity. And the same deal with the sine graph, by the way. So if I take you back to inverse sine, if we were to extend this, kind of tilt our head or turn the paper, and if we didn't stop this graph at those endpoints, if we were to continue that pattern, it would look like sine. It actually looks like a reflection of sine, but it has that same hill and valley pattern to it. And it does look like the reflection of sine, and even if you were to turn it the other way or tilt your head the other way to look at it, you would end up with a reflection of sine as well. Okay, so that's inverse sine and inverse cosine. We actually only have one more to do. We do inverse sine, inverse cosine, and inverse tangent. It is possible to do inverse cotangent, inverse cosecant, and secant, but we don't do those in this class. So last one here is the tangent graph. Looking at tangent, this is not one-to-one. This fails the horizontal line test very badly. So what we're going to do is we're going to focus on this one piece right here. And that's the restricted domain we're going to use. So the restricted domain that we're going to use goes from negative pi over 2 to positive pi over 2. It's similar to sine, it's restricted domain, but it uses parentheses instead of brackets. Because you can't use pi over 2 and negative pi over 2 because that's where the asymptotes are. So it must be parentheses for this one. And this one full period of tangent covers the entire range. So I'm going to zoom in on that piece of tangent. So I'm not up to the inverse yet. And the piece of tangent we're looking at looks like this. Goes through 0, 0. Has a vertical asymptote at x equals pi over 2. And another vertical asymptote at x equals negative pi over 2. And if we want to find the inverse, which is tan inverse or arctan, we're going to switch the domain and range. So the domain will be all real numbers, and the range will be negative pi over 2 to positive pi over 2. And if we use that information to set up our axes, it's actually not very much information at all, because the graph is going to go forever to the left and forever to the right. And it's only the range that has any restrictions. So that's going to be pi over 2, negative pi over 2. And so we set up the axes. Now we're going to reverse the ordered pairs. So I'm going to have 0, 0 here. And that's the only point on the graph that we have labeled. So in order to get the graph of the inverse, we have to use different clues than we used for sine and cosine, because we only have one ordered pair that's nice and clear here. So one option would be to figure out some more ordered pairs, to do like pi over 6 and pi over 4 and pi over 3, and figure out what some other ordered pairs are, and then reverse the x's and y's and plot them. Another option is to think about flipping over this over the line y equals x. Some people will be able to visualize that, and some people won't. I have trouble visualizing that myself. We also have another clue that can help us that we didn't have for sine and cosine, and those are the asymptotes. So if there's a vertical asymptote at x equals pi over 2, since inverses are all about switching x's and y's, there must be a horizontal asymptote at y equals pi over 2. So if tangent has an asymptote at x equals negative pi over 2, then its inverse must have an asymptote at y equals negative pi over 2. And then to figure out how this graph goes in, we need to figure out where it belongs and what the concavity will be. So if you had trouble visualizing the entire thing before, If you picture just this part flipping over the line y equals x, I think you can see it's going to go like this. It's going to go up to the right, concave down, and it's going to be bound by that asymptote. And then if you look at just this piece over here on the left, so don't try to look at the whole thing all at once. Just look at this piece down here. Try to picture that reflecting over the line y equals x. And I think you'll see it's going to be concave up, approaching that asymptote. So some of you are lucky enough to be able to visualize that right from the beginning. Like I said, I have trouble. So the way that I actually remember what inverse tan looks like is I remember who tan reminds me of. Tangent reminds me of x cubed. So x cubed looks like this. And if x cubed looks like that, if you remember the inverse of x cubed is cube root, and if you remember your x cubed and cube root graphs from the earlier in the year, since these are inverses of each other and x cubed kind of reminds me of tangent, then shouldn't tangent's inverse kind of remind me of cube root of x? So that's how I actually remember what arctan looks like. Since tan reminds me of x cubed, its inverse should remind me of cube root of x. So I know that that goes through the origin up to the right, concave down, down to the left, concave up. A big, big difference between these two graphs is that cube root is not bound by asymptotes. This will go up forever unbounded. It goes up very slowly, but it's going to go up, 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 and up, up as high as it wants forever. Whereas arctangent is bound by this asymptote on top. It'll never reach y equals pi over 2 and certainly never exceed it. And this is your graph of arctangent. We're not going to do any transformations to it, but starting tomorrow, we'll start solving some types of problems that use this information from the arctangent graph. Thanks for watching, guys.